Okay, we're going to talk about here the last chapter, which is kinetics, kind of like the experiment we did yesterday. So kinetics deals with really how fast or slow a reaction takes place. So really, we deal a lot with the rate of a reaction when we talk about kinetics. As we saw a little bit yesterday, the rate constant, it sort of tells us again how fast or slow a reaction will sort of occur. So there's kind of two things that we talk about, which is kinetics and thermodynamics, although we don't really talk about thermodynamics in here anymore. But when you take 200B, we'll talk about thermodynamics, and thermodynamics deals with the idea of energy as part of it, also the idea of spontaneity. And really, when you look at sort of thermodynamics, a lot of times what it is sort of trying to answer is whether or not a reaction will take place. And that's really what spontaneous means. And sometimes people confuse a reaction being spontaneous with the idea that it will occur super fast. And that's not necessarily the relationship there. If a reaction is spontaneous, as you'll learn in 200B, when you talk about thermodynamics, if it's spontaneous, it means that under those conditions, the reaction will take place, but it could be really fast. It could be really slow. It could be sort of moderately fast sort of reaction. So there is not necessarily a link between spontaneity necessarily and how fast or slow a reaction takes place. But sometimes, again, in our heads, we think spontaneous and it's just a snap of our fingers is going to sort of occur. And really, that's where kinetics sort of comes into play. Kinetics deals with the idea of sort of how fast or slow a reaction is taking place. And one way that we usually will sort of look at sort of the rate of a reaction is what's sometimes referred to as a reaction rate. And that's really the change in concentration of a reactant or a product with time. And that's really what this units are. This is molarity over seconds. And that's basically how fast the concentration is changing per second, right? And that's a rate, how fast you do something per unit of time, basically. And if we have sort of a generic reaction here of A going to B, we would expect in this case that this reaction should be heading towards the product side, as it is a one-way street. And what we would expect to happen in this case is the reactants should really start to be decreasing with time. Again, in order to make products, you have to use up your reactants. So we should start to see the concentration of our reactants decreasing with time. And on the other side of that is the only way to make products really is to use up some reactants. So over time, we should expect to see our products starting to gain. So really, we should kind of see a decrease in our reactants. We should start to see an increase in our products as this reaction basically starts to occur. And one way that we could sort of express this in terms of a rate is what is sometimes referred to as a rate expression. And that's sort of what these guys are. These are sometimes referred to as a rate expression. And in this case, the rate is equal to minus the change in the concentration of A over time. Again, a reminder that when you see those brackets, that is concentration. And as pretty much molarity is usually what we're talking about in most cases. And the delta is the change. So it's basically the change in the concentration of A over the change in time. And because we would expect it to be decreasing with time, and it's a reactant, we do actually include a negative in front of that. So that negative is there because that is a reactant, because it should be decreasing with time. On the other side, we see our product. We could also do a rate expression for that. The rate is equal to the change in concentration of B over the change in time. As you will notice, there is no negative on the product side. And that is because, typically speaking, these numbers here, these rates, usually is a positive number. And the reason why, obviously, we would also include the negative there on the reactant is because the concentration of our reactant should be decreasing with time, which means if we looked at our initial concentration of A versus our final concentration of A. Our initial concentration, say, was 4 molar, our final was 2 molar. When we do in the change in the concentration of A, we would take final minus initial, which would be 2 minus 4, which would give us minus 2m. That negative and that negative will turn our rate into a positive number. So we don't necessarily need that for our products, because if we looked at the concentration of our product here initially, say versus final, and just making up numbers, 0, say molar, and we had 2 molar, when we do the change in the concentration of B, we would take our final minus our initial, which would give us obviously a positive number there. So we do not need that negative. So the negative is there to basically turn our rate, and that's sometimes referred to as the average rate of the reaction, into a positive number. And that is obviously how you do a change in something, change in time, change in concentration. Obviously, final minus initial is what you want to do so that you get the negative or don't get the negative as you need it. Questions on that there? Now, there's many ways that you can sort of follow kinetics through sort of a reaction. And one way is obviously to record the time, similar to kind of what we did in the experiment yesterday. We're looking for some type of color change, and we basically measured how long it took for that change to occur. And this is what we see just graphically here. To start here, our black circles are our A, our reactants. Our red circles here are our products. And at the very beginning, obviously, you can see we pretty much have 100% reactants, no products. As we go through time, we start to see the appearance of products being made, and obviously more red circles happening all the way through, and obviously less black circles, which represent, again, our reactants decreasing with time. And we see that graphically as well. At the beginning here is pretty much all reactants. But again, we do need to use up our reactants to start making our products. And at the beginning, we have no products. And as we start to make, obviously, our products, we will be using up our reactants in this case. So one very common way that you could do kinetic sort of studies is very similar to some of the procedures that we actually used in previous experiments, particularly when we used that spec 20 and we did like the Kool-Aid experiment where we're following absorbance versus time. Bless you. And here we have this reaction, which is Br2 plus a low formic acid, makes some Br minus, H plus, and CO2. All these guys over here are colorless, but this guy over here obviously has a color. Here it is right there. And at the beginning of the reaction, obviously, we can see we have a pretty dark color there. And as this reaction starts to proceed and we make more products, we're going to make more of a colorless solution. And we know this reaction is proceeding. As you can see, it's kind of a darky orangey red, and then it becomes kind of an orange, more of a yellowish orange, and then obviously to a kind of colorless color at the end there. And that means that the reaction is obviously complete at this point. We would expect probably mainly products happening right about here, as opposed to pretty much all reactants at the very beginning. And if we wanted to sort of study the kinetics of this reaction, we could do so by using something like a spec 20, where, as we talked about, we basically shoot light at a specific wavelength right through our sample. It hits our detector and it measures either absorbance or transmittance. Absorbance, obviously, how much light's being absorbed by the solution. And as we talked about when we did in that Kool-Aid experiment, right, the darker the solution, the more light's going to be absorbed by it. Less of it obviously is going to hit the detector. So we would have a higher absorbance value at the beginning here. And obviously we would have a very low absorbance at this point, probably negative numbers, maybe depending on what you're using, but you would basically zero out. So you would have a pretty high sort of absorbance, and eventually what will happen is it will start to level out. And actually, just by this sort of graph, this linear graph that you will sort of get, you know, kind of come down in terms of absorbance and then sort of level out. You take basically this part of the graph as it's decreasing with time, it will allow you to figure out things like the rate of the reaction and stuff like that by taking something like the slope. When we use anything like this, a couple of things that we did talk about, like in the experiment, where we set the wavelength right to the complementary color to what is being absorbed, right? So what we see. So again, we wouldn't set it to sort of that orangey red sort of wavelength, right? We would set it to its complementary color. We could determine that wavelength that we should set it by doing something like the maximum absorbance, right? And that's what they call the spectrometer, I think, in that experiment did, right? He measured at different wavelength and you found sort of the maximum. So again, here we'd probably want to set our wavelength in this sort of area. Again, that's going to give us a scale where we could test a lot of solutions that are obviously going to be on the scale. Clearly, we wouldn't want to set, as we talked about, our wavelength way over here because that's about all the absorbance you're going to get out of it, and most things will be off of the scale. So it is important, obviously, when you do these type of experiments, to pick the maximum wavelength so that all your samples can do that. And that's usually one of your first steps when you sort of calibrate like the Spec 20 or some nicer sort of units to use. You sort of pick your wavelength and maximum absorbance. When you do these type of experiments, you also would want to always make sure that all measurements were done at the same wavelength. You never want to do them at different wavelengths. So once you pick your maximum wavelengths, kind of like what we did in that experiment, we locked in your maximum wavelength, then you test all your samples, obviously, at that wavelength. So looking at this sort of curve here of this reaction, we can see that with time, the concentration of BR2 is decreasing with time over it. And we do see that decrease. And there's two types of rates that we oftentimes talk about. And most of the time, we do deal with really the average rate. And the average rate is sort of the overall sort of run from beginning to end. We take our final concentration, in this case of BR2 minus our initial, divided by our final time minus our initial time. You also can sort of calculate the instantaneous rate, which is basically the rate at which you're traveling at a specific moment in time. So I sort of compare these to like driving, right? So if you drove from here, say to Arizona or something like that, along the way, overall from beginning to end, maybe you drove like at 70 miles an hour on average, but there are probably points maybe along the way you drove at 65, 70, 75, 85, 90. I'm hoping not much more than that, I suppose. I guess it's 75 once you cross the border. But along the way, if you sort of measured your driving at a specific period of time, hopefully when the cop's not behind you, you would maybe be going faster than say 70 out over there. But if you average out your whole trip, how long you took, maybe you only averaged that trip at 70 miles an hour. So same thing sort of happens with reactions. If you sort of take a sort of shot of a reaction at a specific period of time, it may actually be moving faster or slower at that particular period of time. But again, if you sort of look at the overall sort of run from beginning to end, you'll get this sort of average rate at which it runs. You could get sort of instantaneous rate for a specific period of time by taking the slope of the tangent of that line. Sounds very mathematical. There you go. Now, when we look at this experiment, there is a relationship that we do see when we look at the kinetics of an experiment that is sort of a constant value, and that is the rate constant here. And if we take something like what we see there, which is the rate is equal to K times BR2, this is what is sometimes referred to as a rate law. And the little k is what is known as the rate constant. And it is little k because, as you'll learn, if you do take 200B, capital K is the equilibrium constant, which is much different or a little bit different. So little k there is the rate constant. And as you can see, it does give us, if we sort of solve for the rate constant in this particular example, it would be the rate divided by BR2. And it does give us a constant number. So the rate constant is a constant number for a particular reaction at a specific temperature. And it will basically be constant no matter sort of how many experiments that you sort of do. In this particular case is 3.5 times 10 to the minus 3 reciprocal seconds. That number is not so important or anything like that. But what we will talk about is actually the units associated with the rate constants that you see are actually important sort of values. They will tell you what type of reaction you're dealing with. Is it a first order reaction, second order, or zero order reaction in terms of how things are reacting together? So the rate constant is given to you. You could think of the rate constant again as sort of how fast or slow a reaction takes place. So the larger the rate constant, you typically will have a faster reaction. So to lower the rate constant, a sort of slower reaction will take place. Now, in a case where perhaps we are not getting any type of solution that makes a color, either starting with a color or ending with a color, we sometimes have to look at other ways to measure the rate that's going on. So in this particular reaction, this decomposition of hydrogen peroxide, it will make water and oxygen gas, which is all colorless. So using something like spectrophotometry or like a spec 20 like we used in that Kool-Aid experiment would be pretty much useless in this type of experiment because you have no color, which means every time you would measure absorbance values, you would get zero basically because nothing would be absorbing. So there's no way to really follow it. So in situations like this, we can look at other things. And in this particular case, we are generating a gas. And this gas is oxygen. And since it is a gas, we can follow the change in pressure in this case. And we can use our ideal gas law here that we've seen. And as we talked about a couple of times, if we do solve for N over V, that is P over RT, right? And in the ideal gas law, right, the units of N is moles and the units of volume is liters, which is the molarity. And as we saw, I think when we were talking about colligative properties and so forth, that is basically the molarity of the gas. So in this particular case, if we were to do this experiment, really, we probably would have the temperature being constant, R is a gas constant, which means we could very easily, by just looking at the change in pressure, which is something that we can measure, we can basically relate it to the molarity of the gases being produced. This would be good because in this particular reaction, the only gas that's being produced is oxygen. There's no gas anywhere else, which means all the pressure that should happen in this sort of reaction should come from the oxygen that's being generated. And that means if you have no pressure, you haven't made any product, right? And once you start to see pressure, you obviously have started to make some products. So we could see by that increase in pressure in this particular case that with this reaction would be taking place. And again, we could do an aspect of time as well with that. So if we insert that in there and just move the P over, that's basically our P over RT and also the change in time. So we could actually figure out the rate at which the oxygen is being produced in this case by simply following the change in pressure and over a period of time. And that will allow us to figure out the rate here. So even in an experiment where maybe you can't take advantage of absorbance values and stuff like that because there is no colors in any of these solutions or substances, we could still look at pressure and sort of use the ideal gas law to follow the rate at which a gas is being produced. So let's talk a little bit about stoichiometry and rates of reactions because we cannot forget about our friend stoichiometry, and it does come into account and have an effect on the rates of reactions in terms of sort of the moles to moles of how these things are reacting with one another. So if we have this reaction, we know from this sort of equation here that basically for every 2 moles of A, we get 1 mole of B that's basically being produced. So we do need to incorporate that into sort of our kinetics sort of equations and our rate expression. So in this case, if we were looking at our reactant here, the rate would equal minus, again, because it's a reactant, 1 over 2. And the 2 is the coefficient. So by taking 1 over the coefficient, it will take into account the stoichiometry in the equation, change in concentration of time over change the concentration of A over change of time. We also could do it for B. The rate is equal to the coefficient here is actually 1. So that would be like 1 over 1, which is 1, which is why there's no numbers or anything there. And it would be the change in the concentration of B over the change in time. And once again, we do not have the negative there on the product side, but we do have it on the reactant side. And again, this rate and this rate and this rate, they're all the same rate. Yeah. And they're basically the average rate for that reaction. And again, that should be a positive number when you calculate it, is typically what that number is. So in general, if we have a generic sort of reaction here of A to A plus B to B goes to C to C, we basically take 1 over the coefficient, and that will take into account all of the multiple relationship for you. And you can do it all sort of in one calculation. You also could, if you wanted to, in some of these problems, just do the stoichiometry part first, do kind of the multiple relationship part first, and then sort of do the kinetics part of the calculation. So you can do it both ways. If you do it this way, where you take 1 over the coefficient, it sort of ties it together and does it together, the calculation. But again, you could separate it out. And if you, again, what you would probably have is some type of information about somebody in the reaction. And you would use that sort of molar-molar relationship to go to somebody else. The rate expression, which is what this is sometimes referred to, is very useful because, frankly, as I just mentioned, you pretty much just need to know one piece of information about the reaction, and you pretty much can figure out how everybody is changing over time. So, for example, if I did know the average rate of the reaction, I could figure out how A, B, C, and D are changing with time. If I just knew about B, for example, how B is changing in that reaction, I could use this relationship to figure out how A is changing, C is changing, D is changing. Now, although they are all put together here, you can just pick out the two maybe that you're interested in. So, for example, let's say we were given some information about D and we want to know about A. We could just pull those out and use those relationships sort of separate to each other. 1 over D, change the concentration of D over change in time. And we could write two kind of separate rate expressions for the two that we're interested in. And again, what sort of ties these guys together is the idea that the rate there, here, and here is the same. So that means if I do know how D is changing, I could very easily figure out the rate, average rate for the reaction. Once I have the average rate of the reaction, I could use that to figure out how A is changing. So that is basically what ties kind of both of those things together, and how we could pretty much figure out how everybody's changing simply by just knowing really one piece of information about the reaction. Any questions on that there? All right, so take a moment here, write the rate expression for this reaction and see what you come up with. Okay, let's take a look. So again, to write the rate expression, we're going to go with the rate is equal to, and we're going to start with our first reactant here, and the coefficient is 1, so that basically be minus 1 over 1. We do need the negative because it is a reactant that changes in the concentration of CH4 over the change in time. That could equal, our coefficient here for O2 is a 2, so it will also be a negative because it's a reactant, so it should be decreasing with time. 1 over the coefficient, that will take into account all the stoichiometry part of it, change in the concentration of O2 over the change in time. Going to our product side, once again, we have a coefficient of 1. On our product side, it should be increasing with time, so they're going to be positive, so we don't use the negative here. This would be the change in the concentration of CO2 over the change in time. And that will equal our coefficient of 1 over 2 change in concentration of H2O over the change in time. Now, I again wrote them all sort of tied together, but if you needed to in a problem, you could just pull out whichever ones that you need. And again, they're all equal to each other, which allows you obviously to relate them all to each other. Any questions on that there? All right, so why don't you try a calculation here with some numbers. For this reaction, the concentration of I goes from 1 to 0.868 in the first 10 seconds. Calculate the average rate in the first 10 seconds, and what is the concentration of H plus over time? How is basically H plus changing over time? So take a few moments to see what you get here. Again, use your rate expression there to sort of solve for that. All right, let's take a look and see. So in this case, we have our I minus, and we have some information about it. So the concentration I minus initially was 1 molar. Its final concentration here is 0.868 molar, and their time is really 10 seconds, our initial 0 and final 10, basically. We are interested in the rate. We're also interested in H plus as well. So there's two sort of rate expressions that we could kind of pull from this equation. The rate of I minus would be minus 1 over 3 change in the concentration of I minus over the change in time. Once again, the 3 here from the coefficient. And we also have that the rate for our H plus is equal to minus 1 over 2 for the coefficient. The change in the concentration of H plus over the change in time. Again, the thing that sort of ties both of those together is the rate there. So that is the average rate. So since we really do have enough information for the I minus, we could just put our numbers really into this sort of formula here first and get the average rate. So let's do that. So if we look at the I minus first, the rate will equal minus 1 over 3. Again, here, our final concentration of I minus is 0.868 minus our initial, which is 1. And again, our time would be basically 10 minus 0 seconds in this particular case. This is important because, again, this part right here is going to give us a negative number, which is why we have the negative here. We'll turn, again, our rate into a positive number in this case. And if we do that, that's 0.868 minus 1 divided by 10 and also divided by 3 for the coefficient. Going to give us a rate here, or average rate for this reaction, 0.020044. The units here are molarity over second, or the units. That is the average rate for this reaction. Any question on that calculation there? Now, again, that rate is this rate right here. It is also this rate right here, which means now that we have the average rate for the reaction, we could use our rate expression for H plus to figure out how it is changing. So for our H plus, the rate is equal to minus 1 over 2, the change in the concentration of H plus over the change in time. And in this particular case, we were actually interested in this part of it, which means that we do need to multiply to the other side the 2. This is also why doing the 1 over 2 is good, because you could hopefully see you need to multiply and not divide, which is sometimes what people mess up on. And it's not only the 2 that needs to go to the other side, but it also is the negative that needs to go to the other side. So basically, when we multiply that to the other side, we end up with something like this. And since we already know the rate is that number right there, that gives us something like this. And that obviously then gives us something like minus 0.0088 molar seconds. And here we actually do end up with a negative value, and that is because in this case, H plus is a reactant, which means it should be decreasing with time. So the negative actually does stay here in this case, because it's not the average rate for the overall reaction, but we're talking specifically about how H plus is changing with time. So that negative tells us it's decreasing basically every second, a molarity of 0.0088, which means based on the stoichiometry that we see there, it is doing basically twice as fast as the average rate of everybody, right? The entire reaction is, right? It's moving twice as fast because there's twice as much, right? So you lose twice as much of it. Any questions on that calculation there? All right, so let's try this one. If 2.4 times 10 to the 2 grams of NOBR, molar mass from the periodic table, 109.9 grams per mole, that comes from the periodic table, decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes. Find the average rate of BR2 production. So see what you come. All right, let's take a look. So in this case, we're given information about NOBR. We're also interested in the BR2. So if we want to just kind of pull out our 2 rate expressions, our rate will equal minus 1 over 2, the change in the concentration of NOBR over time. And for our BR2 there, our rate would equal the change in the concentration of BR2 over the change in time. Once again, this guy is positive and the coefficient is 1, so that's why there's nothing there. Again, the other one, a reactant. In this case, we do have information about really how NOBR is changing with time. We do have to do a little bit of work here. We do need molarity, and we also need our time. So first off, to get basically our change in our concentration of NOBR, to get to the concentration, we're going to take our grams of it. Going to use the molar mass there from the periodic table, or they were nice enough to give it to us, which is good. Grams per mole. And that will get us 2.4 to the 2 divided by 109.91, about 2.1836 moles. We have to turn that into molarity. So basically here we have 200 milliliters, which is 0.2 liters, is basically converting that into liters. So really the concentration of NOBR would be 2.1836 moles divided by our liters. Going to give us 10.918 molar. That is basically how the concentration is changing with time. Now, in terms of our time, it is in minutes, and ultimately we do want our time in seconds. So at some point you need to do a conversion. So I'm just going to convert that straight up right away. So that's going to give me 5 minutes. A minute is 60 seconds. That'll be 300 seconds here. So now I could actually use that to get the rate part here. So now putting that into our rate expression, our rate is equal minus 1/2. Our change in concentration is going to be negative 10.918 molar over really our change in time, which would be 300 seconds. I put a negative here because this is a reactant, which means it should be decreasing with time, even though they didn't straight up tell us. But again, that gets us to a positive rate, basically. So putting all that in is going to give us a average rate for this reaction of about 0.0182 molar seconds if I used the rounded numbers in that particular case. Now, once I know the rate here of the reaction, I could use that to relate it to my BR2. And we saw earlier that the rate is equal to the change in BR2 over the change in time, which means pretty much that is that number right there, which means it would be the same number here for our BR2 in this particular case, as it's a 1-to-1 relationship there in that particular case between the rate basically and how that is changing. Any questions on that there? So doing 1 over the coefficient does the stoichiometry for you. As I mentioned earlier, if you wanted to, you could approach it more as a stoichiometry problem and then do the kinetics part of it. So for example, here where we have moles of our NOBR, you could have at that point just took your moles of your NOBR and just did a regular stoichiometry move, which is from the equation, there's 2 moles of NOBR, 1 mole of BR2. That would then get you 2.1836 divided by 2, get you 1.0918 moles of BR2. At that point, you then could put in all the rest of the stuff that we had, which was the 0.2 liters divided by 0.2 gives us 5.459 molar. You could divide it by the time, which was 300 seconds. And that gets you to 0.0182 molar seconds. So if you want to take just kind of a more stoichiometry approach first and then kind of input all the kinetics part of it, you could do that mole to mole, or you could do 1 over the coefficient, kind of does it all together in one part of the calculation. Any questions on that there? Yeah. I added a negative because NOBR is a reactant, so it should be decreasing with time. So normally how we would have got that, we got that number where it was 10 point something. So the way we would have got that number would have been taking final minus initial concentration. And that should, in this case, because it's a reactant, end up being a negative number. We just kind of had the end product of that sort of subtraction. And if we don't put it in, what we would end up with is a negative overall rate here. And then this would be a negative at the back end, which means the BR2 shouldn't be negative because it's a product, so it should be increasing with time. So that's why it was important to kind of insert that. In most cases, if you have both of those numbers, kind of the final initial, you would get the negative just by the calculation. But here we had kind of the answer to that calculation, so we had to kind of insert it. So we got negative now. Other questions? Okay. So what we're looking at here is what is referred to as the rate expression. And again, it allows you basically to figure out how everybody's changing the reaction. Again, you pretty much just need one piece of information and you could tie how everybody is changing in that particular reaction. Now, speaking of reaction rates, there are several things that affect the reaction rate. The nature of the reactants plays a role in how fast or slow a reaction may take place. Smaller molecules do react faster than larger molecules. Gases will react faster than liquids, and usually liquids will react faster than solids. And that also is related to energy, right? If you're in the gas phase, they're broken apart from each other, they're flying around, they have a lot of energy, so they're good to go when the reaction takes place. Remember that for a reaction to take place, there has to be a minimum amount of energy that occurs when things collide with each other. So not all collisions of, say, molecules together will result in products being formed. They do have to hit each other with the right amount of energy. So obviously gas molecules have a good amount of energy. So a lot of times that are able to react pretty good. Obviously in the solid state, they're not reacting as much with a lot less energy. So usually a lot slower sort of reacting. Powdered solids are more reactive usually than blocks. And again, it gives a greater surface area for those things to react. There are activity series of metals that we talked about when we talked about single replacement reactions. Again, there are certain metals that are more reactive than others. Same thing with our non-metals as well, right? Our reactivity increases, say in group 7 as you go up. Ions are much more reactive than molecules because ions are basically floating around in solution, which means they're good to go. They're just floating around ready to react. So they are good to react. Temperature plays a really big effect on the rates of reactions. So increasing the temperature typically will increase the rate of the reaction. And vice versa. Obviously, if you decrease the temperature, usually will slow down the reaction. Although we didn't do it yesterday, that's what the ice bath and the hot water bath was for. So if we stuck our sort of flask into the hot water bath, we should have saw it sort of turn blue a lot quicker. If we threw those guys all into ice and sort of cooled down the temperature, we would have saw it occur a lot longer of a wait in that particular example. In general, if you raise the temperature of a reaction by 10 degrees Celsius in a lot of reactions, not all of them, but in a lot of reactions, it will double the rate of the reaction. The Arrhenius equation is something we will take a look at a little bit later on in this chapter. It relates basically rates to temperature. Other things that can affect a rate of reaction are catalysts, and a reminder that catalysts are not reactants. They are not products, and they do not get used up in a reaction. Really, catalysts are there to facilitate that reaction occurring a lot faster. A lot of times it finds sort of an alternative pathway for that reaction to take place, and thus usually will speed up a reaction. There are certain catalysts that are used sometimes to slow down a reaction, but probably 9 times out of 10, somebody's talking about a catalyst, they're probably talking about it in terms of speeding up the reaction. In chemical equations, we oftentimes can find catalysts a lot of times written on top of the arrow, where you see things like PT or H plus or things like that. That's usually where they're written in equations. There's a couple of different types of catalysts. There's homogeneous catalysts, which means that basically the catalyst and the reactants are all in the same phase. Maybe they're all aqueous. So for example, if we use acid as a catalyst for a reaction, or base as a catalyst for a reaction, they would all be sort of in the same phase. Heterogeneous means that they're in different phases. So for example, if we use something like a metal, metal obviously is in a different phase than say gases that may be flying around. So for example, one way a catalyst sort of works is, for example, if you did have like a metal that's used as a catalyst, so a lot of times what will happen is those gas molecules flying around will be more attracted towards the metal. So they'll all kind of congregate on the metal, which means they're all within each other very closely and can allow them all to start to react a lot faster than if that metal wasn't there and they're just kind of flying around trying to find each other. So sometimes it creates sort of a platform for everybody to kind of get together in a much more efficient manner than it would if it wasn't there to facilitate that reaction sort of taking place. Concentration also plays a tremendous role in the rate of a reaction, and generally the larger the concentration, the more or faster the reaction will come in contact. And that's because when we look at something like concentration, say like molarity, which is moles of solute over liters of solution, when we have something in a solution, for example, that's reacting, it is the solute that really is doing the reaction. Remember, the solute's really the name of the solution. So again, if you had like a sodium chloride solution, it is the sodium chloride that's in there that's ready to react and stuff like that. So the larger the concentration, that would mean, just mathematically speaking, we would have a much larger number up on top, which means we would have a lot more moles of your solute floating around in the solution, ready to react, and increasing the rates of collisions of those guys, and also increasing the reactivity that occurs. Gases depends on partial pressure. So the higher the pressure, the higher the concentration. That also relates to volume as well, right? Because as we know, the higher the pressure, smaller the volume. So now we got gas molecules in a much smaller volume, which means they're much more concentrated with each other. They're also near each other a lot more and going to allow them to react with one another a lot easier. So let's talk a little bit about the rate expression, not rate expression, the rate law, which is a little bit different than the rate expression that we were just talking about. So the rate expression that we were just talking about really deals with sort of the overall reaction as a whole, and how everybody is sort of changing. The rate law basically expresses the relationship of the reactants raised to some type of power. So if we have this equation, this would be sort of our rate law. The rate would equal K, which is our rate constant. And again, that is constant for a reaction at a specific temperature. These again are our concentrations, which most of the time is molarity. And X and Y are the orders. So X in this particular example would be the order with respect to A. Y would be the order with respect to B. And you could figure out the overall order of a reaction by adding those guys together. So if they both are ones, the overall order would be second order. If they were like a 2 and a 1, then it would be third order, or 0 and a 1, it would be first order, for example. Now, again, the orders are found experimentally. So the orders are always found experimentally. So they are not the coefficients in the balanced equation, which sometimes people get confused on. Sometimes they are the same number, but that is not how you get that number. You just don't take it from the coefficient from the balanced equation. You actually have to calculate it through some calculations that we talked a little bit about yesterday, and we'll talk about here again today. So what do these orders sort of tell us, or the overall order of the reaction? Well, the orders sort of tell us, again, sort of the proportion that you need of these reactants, basically to sustain a specific rate. Also important in the rate law is it is all about reactants. So you don't put products in the rate law. So it's all about A and B in this case. C and D are not included in the rate law. So when you write a rate law, different than a rate expression, it's all about the reactants and how they are doing it. So how does a rate law sort of help us in sort of real life? So let's just say, for example, we had this and we said that the rate, we determined that the rate law for this reaction is A is to the first power and B is to the first power. Usually we want to write the ones, but we'll just write it here for example. The overall order here would be basically second order. And we would get that by taking 1 + 1, basically. So we would add these orders together, and that would tell us that overall this reaction is a second order reaction, which is important to know because it will deal with some specific types of equations later on. So let's just say that we initially had a concentration of A that was 2 molar, and we had B that was 2 molar, right? So if we sort of put this into this rate law here, we would get basically the rate is equal to 2 times 2, basically. We're going to ignore the K because it's a constant. So whatever that number is, it doesn't really matter in the set. That gives us sort of a rate of, we'll call it 4 molars per second. Now, let's just say in this experiment, we decided, all right, we're going to then increase the amount of B. We're going to double the amount of B in this reaction. So we do this experiment again, and the second time around, we have A is 2 molar, and we'll take B and we'll actually double the amount, our concentration of it that we use. Now, when we put it into our rate law, we basically get 2 times 4 in this case, which means our rate is like 8 molar per second. What we see in this reaction is if this was the rate law, when I doubled the amount of B, what happened to my rate? It also doubled, right? So I basically increased my rate, right, of this reaction. I sped up this reaction by just doubling B. The same thing would happen if I doubled A and kept B the same, right? It would also speed up the reaction by a factor of 2. So if I do this reaction, it's taking a long time, and I want to kind of get it going a little bit quicker, I could, in this case, just double B, and it will basically double how fast this reaction takes place. Now, sometimes when you do kinetics experiments, you do it and it's like you're like way too slow to kind of measure something. So by the time you get it, say, into the spec 20, the reaction's over and all you guys like a flat line, no absorbance, everybody's dead basically at that point. And you go, well, this is like way too fast to measure. Maybe I want to actually slow this reaction down instead of speed it up. So if I decide, hey, I want to actually slow this reaction down, let's say I did this equation again, a reaction again, and I kept A at 2, but I decided I'm just going to cut B's concentration originally down in half to 1 molar. Now, when I do my rate sort of calculation, I'm basically taking 2 times 1, which gives us something like 2 molar seconds. So I cut BA in half from where it started, right? And it went from like 4 molar seconds down to 2 molar seconds. So I just effectively slowed this reaction down by half by changing the concentrations. So understanding the orders of how these reactants basically need to be or how they are working in this particular reaction allows you to practically, if something is moving too fast for you, you could kind of play with the concentrations and you could find a way to either speed up the reaction or slow it down. Any questions on that? Why it's important how this rates and orders are for a reaction is it has also an effect, obviously, when you do something like that. So, for example, let's say we did this same reaction, but we originally found that the rate law here was not the orders of 1 and 1, but let's just say that our rate for this guy was K times A to the 1 and B to the 2, our second order. That means in this case, our overall reaction would be 1 plus 2, which would be third order. Right? Now, in this particular case, if I did the same 3 experiments that I did originally, which was my concentration of A is 2, and my concentration of B is 2. When I put this into my rate law now, I get basically 2 times 2 squared, right? And that's basically just putting those 2's into the concentration. Here I'm ignoring K because it's a constant, so it could be whatever number, just be constant, all these things here. That means in this case, that's 2 squared, which is 4 times 2 is 8 molar seconds. Now, this same sort of reaction, but because the orders are different, right? Using the same concentrations, I went from a rate of 4 in that original one when everybody was first order to, in this case, because B is second order, we now have twice as fast this reaction is taking place versus the 2, right? And if I decide, hey, I want it to maybe occur faster, and I do the same thing, I increase my B to say 4 molar. That's now going to give me a rate is equal to basically 2 times 4 squared. It's a lot of math, but that's 16, I think, and 2 is 32. Yeah, 32 molar seconds, right? In this case, I doubled my concentration of B, but my reaction went up by a factor of 4. Yeah. So, and that's because the order for B is 2, right? That is different than in this, if I did my A, where I doubled the concentration to 4 molar, and my B I kept at 2 molar. In this case, my rate would equal 4 times 2 squared, which would give me 4 times 4 is 2, right? Which is 4 times 4, not sorry, 2 times 2 is 2 squared. I'm gonna spit that right. 2 squared is 4, 4 times 4 is 16. There we go. Gives me 16 molar seconds. In this case, by changing the concentration of A in this reaction, by doubling it, I only saw a increase in the rate of 2, right? But by doubling B, because its order was 2, I actually saw a much larger increase. So if you want to speed up this reaction really fast, you would play with B, right? It has a greater effect on the overall rate than A in this example. If you wanted to just moderately maybe increase it, you would play with A, right? Just concentration to speed it up. The same thing would happen if we decrease the concentration. Obviously, if we decrease the concentration of B down to 1 in this example, that would give me effectively a rate that's equal to 2 times 1 squared, which would still give me a 2 molar per second, which is a decrease, right, in the rate of about 4-fold. So again, by knowing the orders, you could also see how you could play with the concentrations to either speed up the reaction, slow down the reaction. You could also see which one has a greater effect, obviously, on the rate. In this case, versus A and B on my second example there, B has a much greater effect on the overall rate of the reaction than A does. So you could say with either one. Now, what happens if I had a rate law that looks something like this, where K was A to the 0 and B, say, to the 2? Something to the 0 order is equal to 1. Yeah, so something to 0 order is equal to 1. Now, in this particular case, if I increase the amount of A, say 6-fold, would it have an effect on the rate? It would not, right? Because basically it's 1. So you can do as much as you want in this particular reaction to A, and it's not going to have any effect on the rate. In this case, you would have to only do something to B if you wanted to speed it up or slow it down. Any questions on the orders and sort of how they practically can help you understand or adjust sort of the rate of the reaction? All right, so let's talk about how we actually calculate a rate law. So as I mentioned before, rate laws are typically, and orders are found experimentally, and really rate laws are found experimentally. So a lot of times what you will end up with is a table such as this. And this is very similar to sort of like the table you had yesterday in the experiment, where you had basically the concentrations and you have the time that it occurs. And typically what you will find in these tables are the concentrations of the reactants, and you'll find what is sometimes referred to as the initial rates. And you could use this information in these tables to basically figure out the rate law for a particular reaction. And this is commonly how you do it. Now, most people, mathematically is probably the easier approach to do versus just looking at the numbers. So we'll talk about mathematically how to do it. And you basically could use this formula that I put up, I think, yesterday as well. The rate 2 over rate 1 is equal to K times A to the X and B to the Y, and K A to the X and B to the Y. So basically what we want to do when we go to a table like this, and it may have 3 entries like this, it may have 4 or 5, it may have a ton of different sort of experiments. We want to choose basically 2 entries where one of the concentrations remain the same and the other one varies. And what that's going to do is basically give us only one unknown at a time. So in this particular case here, if we were to write our generic rate law for this, the rate would equal K times F2 times ClO2, and this would be to the X and to the Y here. We're going to try to find X and Y here in this calculation. So looking at this table, I can see that if I looked at experiment 1 and experiment 2 here, the concentration of F2 stays the same, but the concentration of our other reactant does vary. So that's going to allow me to figure out the order for our Cl2. Now, I personally go this way. You don't have to, it'll come out the same, but I personally will choose whichever one has the larger rate and put it up on top. And a lot of times if you do that, you will end up with larger numbers, more whole numbers. If you do it the opposite way, you get some decimals. It works out the same if you do the math correctly, but so sometimes it's easier to see the larger numbers than maybe some decimal numbers. So for me, I'm going to put everything from experiment 2 up on top of this equation, basically. So that means that my rate in this case, if we looked at experiments 1 and 2, my rate for the second one is 4.8 times 10 to the minus 3 equals my K. My concentration of A in that one is 0.1 to the X. My concentration of really my second reactant there is 0.04 to the Y. So everything that I put up there all came from experiment 2 in that table, all that information. And now I'm going to put everything from experiment 1 on the bottom, and that would give me a rate of 1.2 times 10 to the minus 3. My K, my 0.1, and my 0.01 to the Y. And again, everything in blue came from right there, experiment 2. Any questions on that there? So now we're going to do some math here. So when we divide this out, that's going to give us a 4 is equal to, when we come to the other side, this up on top and this on the bottom, they are both K's. They are both rate constants. And by the name of it, constant means, although we don't know what the number is right at this moment, it is the same number up on top and bottom, which means they should cancel. Basically give us a 1. Now, when we get over here to the orders, that is the order of X with respect to F2. Although we do not know what it is at this moment, we do know that it should be the same number up on top and bottom, which means this also will cancel out completely. And here, if we come to our next guy, we're going to divide that, and that's going to give us 4 to the Y, basically dividing 0.04 by 0.01, right? Will give us 4. In this case, you could see that Y should equal 1 in this case. By the way, if you're not sure how to really do that, or you don't have really pretty numbers, or you got some decimal type numbers, a little natural log of both sides will do it for you. So when you take the natural log of both sides, the Y comes down, and just divide that out to the other side, and you will get Y is equal to 1, basically. So if you don't have pretty numbers, or you can't kind of visually see it, natural log of both sides and then divide them will get you what you need. Any questions on that there? Now that we figured out the order with respect to the ClO2, we're now going to go back to our table. And now what we want to do is basically find 2 places where the ClO2 stays constant and the F2 varies. And in this case, it looks like experiment 1 and experiment 3 will do that for us. In experiment 1 and experiment 3, the concentration of the ClO2 stays the same. The other one varies. So we're going to do the same calculation, experiment 3 and 1 here. And once again, I'm going to choose the larger value to put up on top. So that's for me is experiment 3. So that's going to give me a 2.4 times 10 to the minus 3 equals K 0.2 to the X, 0.01 to the Y. Once again, all of that came from the third entry in the table. We're going to divide that by the first entry in the table. And that will give me 1.2 times 10 to the minus 3, K, 0.1 to the X, and 0.01 to the Y in this case. Any questions on where any of those numbers came from? Again, they just came from the table, keeping obviously all the numbers together there. Doing our math, this is going to give us a 2. Once again, our K's will cancel. This here will give us a 2 to the X, and this will completely cancel out. Once again, here you could probably visually see in this case, X is equal to 1. Again, it won't always equal 1s on both of them, but in this case, it did. Any question on that? Again, you take the natural log of 2 equals the natural log of 2 times X and divide them out and get 1. Now that we have the orders for everybody, we could actually complete our rate law here. Our rate law would look like the rate is equal to K times F2 times ClO2. And again, much like most things in chemistry, if there's nothing written above these things, it's assumed to be 1 for each of these. So again, the order here is assumed to be 1. Usually you don't write the ones, any other number you write, but usually you don't write the ones here. That means that the overall order here for this reaction is 1 plus 1, which means overall this reaction is a second order reaction in this particular case. Now, once we've actually determined the orders for the reaction or the reactants, what we can do next is actually use our rate law that has the orders to actually calculate the value of the rate constant. So once we get the orders, we can now use the rate law to calculate the value of the rate constant. So in this case, if we took this guy and we solve for K, it would be the rate is divided by F2's concentration and ClO2's concentration. Where do we get those numbers from? We get the numbers from the table. You could actually choose any entry in the table and they should give you the same number because it's a rate constant. So it should be the same number for every entry in there. The only thing you can't do is mix and match. So you got to either choose all the stuff from experiment 1, all the stuff from experiment 2, all the stuff from experiment 3. So for me, I'm just going to choose the stuff from experiment 1. And that means that the rate would be 1.2 times 10 to the minus 3 molar seconds divided by the concentration of F2, which is 0.1 molar, times ClO2, which is 0.01 molar in this case. And if I do that, I have 1.2 to the minus 3 divided by 0.1 divided by 0.01. Going to give me a rate constant of 1.2. The units here are molarity up on top and bottom cancel. There's still a molarity on the bottom, 1 over molar seconds, or you can write 1.2 m to the minus 1 s to the minus is 1 in this particular case. Now these units here are the units you typically find in a second order reaction. And again, that's the units of the rate constant. Question on that. So this is experimentally how you determine a rate law and the orders. And again, you basically want to keep the unknowns to 1 at a time, get the orders, and then you can find the rate constant. Any questions on that calculation? Yeah. I didn't know what the units were. Is that what you're asking? Yeah. So if we look at just the calculation that we did here when we did this calculation, if we just look at the units, the rate from the table is basically molarity over seconds. And each of those concentrations on the bottom were both in molarity, basically. So when we do just look at the units, basically that's molarity up on top and molarity on the bottom. So they cancel each other out. And basically this second is the same as having the second on the bottom. So basically you end up with 1 over molar seconds in that particular case because of it. No, that's actually the specific units that you see for a second order reaction overall. So earlier we determined that this reaction overall, the entire reaction was referred to as being a second order reaction. And that is typically the units for the rate constant for a second order reaction that you see. It's usually 1 over molar seconds, because a lot of times we do reactions in seconds, but it can be really any unit of time. It could be like minutes, hours, it doesn't really matter, but usually 1 over molar, some type of units of time is usually what you find for a second order reaction overall. A first order reaction, for example, if it was like a first order overall reaction, the units that you would see for K is typically 1 over seconds or reciprocal seconds, are really 1 over some unit of time is typically what you see for a first order reaction. So a lot of times in kinetics, there's different equations and formulas that you use if it's say a first order reaction versus a second versus a 0 order reaction. And a lot of times in kinetics problems, they won't straight up tell you, hey, this is first order or this is second order or something like that. But they will, for example, give you the value of the rate constant, and the units that you see with the rate constant will oftentimes tell you, oh, this is like second order, I should use those equations, or this is first order, I should use those. Other questions? All right, so as we saw there, the rate laws are always determined experimentally. And you will always be given this type of table to do. The reaction order is defined, again, really in terms of rate laws, only about the reactants. Products really do not play into rate laws. And the order of the reactants are not the coefficients that we find in the balance equation. As we can see in this example, the coefficient for ClO2 is a 2, and here it ended up being an order of 1. All right. So the rate equation for this reaction of NO is the rate equal to K NO times O3. If the rate is 6.6 times 10 to minus 5 molar seconds, when the concentrations are those, what is the rate constant? So see what you come up with on that one. Okay, let's take a look. So they gave us the rate law here, which is this guy. And in this particular case, we are given the O3 and the NO concentration, and we also have the rate. So we're just going to rearrange and solve for this. This would be the rate is divided by NO and O3. Obviously, as well, if these guys were different than first order in each of them, right? This is basically first order, which means overall here, this is going to be another second order overall sort of reaction. But if these individual reactants were, say, second order or something like that, you would also need to make sure you include it obviously down here, because that would affect the math, right? So you would have to do the squaring or something like that if you did. But in this case, since they're both first order, we don't have to worry too much about that. We're just going to put our numbers in: 6.60 times 10 to the minus 5 molar seconds divided by our NO, which is 1 times 10 to the minus 6 molar. And our 3 times 10 to the minus 6 molar in this case. And we will end up with 6.6 to the minus 5 divided by 1 to the minus 6 divided by 3 to the minus 6. You're going to give us too many zeros to count. I think 2.2 times 10 to the 7. Once again, here the units molarity and molarity will cancel. It's going to leave us 1 over molar seconds, I believe. In this case, any questions on